Okay. Ghetto, are we live? Can't tell. Okay, maybe we're live. Okay, we'll assume we're live. So we're doing we're playing with image generation using the principal component. I mean, so basically we're just playing with the idea of you can, I mean, empirically, like not even intuitively, you can take a collection of images such as these and like these images here, and you can like scale them, meaning like you multiply each pixel by a scalar value, and then you can sum the images, and then you can like get other images. So that's because it's kind of like, if you'd like to understand how like a generative neural network works, I mean, it seems to be kind of using the same ideas, although I mean, they use like convolutions, but like you can interpret a convolution as like as a matrix multiply, I think. So anyway, like we're not explicitly dealing with neural nets today. We're dealing with just linear combinations of images and how they generate other images. So kind of in particular, the main thing I wanted to do was this idea of if I have like an image represented like in the PC basis, it's kind of like, if you don't know what like principal components are, like it's fine. It's like, I mean, literally you can use like random images, but these are, so like these are like the principal component images, and every single one of these images up here, like these squares, can, are a linear combination of the images below. And so yeah, we kind of just wanted to visualize the idea of like, if I systematically alter the weight on like one of the principal component images, how does that like alter the output image? So yeah, let me just like go through exactly what all we're doing here. So the first thing we're doing is we're generating squares. So that is these. This is our data set. Like this is the data set we're using. So these are images of squares, where the squares are translated, like up and down. So this generates that data, and then this draws that data, and then we have to reshape the images to one-dimensional vectors. Then we remove the mean, which I think is like a pre-processing step for principal component decomposition, although I don't think it's like strictly necessary. And then anyway, we just call NumPy linear algebra singular value decomposition. And I've kind of forgotten like the specifics of everything that's happening here, but it returns like three, what is it? Oh yeah, it returns like three matrices One of which is the principal components, which are, so the next thing we do is we explicitly visualize the principal components. So these are the principal components, they're just images, and we're just saying, like, you know, every one of these images, one of the data images, is a literal linear combination of the principal component images. So I think we can, I mean, just, I guess, to drive that point home some more. So these are reconstructions of the original data using only, I think, like the first 9 principal components. So let me see if I can find where that code is. Yeah, so how do we do the reconstruction? Okay, so we first compute so basically what you're doing is, like, for each image, each real image, you're projecting it onto each of the principal components. So that's just like a scalar value. So this matrix multiplication gives you, for each real data image, its PC representation, which is just a vector. And like, you can explicitly visualize that, like, here. So these are like the first 9 principal components for each of the real data images, and these are like how these are how those weights, like, individually vary for each of the real data images. And then if you use the the first 9 components, and then you reconstruct the data, you get this, which is obviously not identical to the original data, but, like, it's close. So the thing we want to do in this video is, like, find the PC representation of a real image. And then, right, so the PC representation is just this set of weights. And so then we just want to, like, systematically vary the weights for, like, a real image. So that's what we're going to do. So, like, varying the PC weights for a real image. So we're going to arbitrarily select a real image. Say that image. And okay, it's saying we're back. I can't believe my internet keeps dropping. I mean, okay, I think we're back. Maybe? Yeah, we'll say we're back, I guess. Okay, so varying the PC weights for a real image. So the first thing we wanted to do is, like, just show the real image. So let's try to, like, see, does this work? Oh, it does. So let's say I want, like, I don't know, like 5, 6. Okay, there you go. That's a real image. And it's a very cool image. Okay, so I'm going to call this real image. And also, like, what is the shape of this? Or even just show the whole image. Yeah. Okay, so yeah, it's literally a binary image. And yeah, okay, I need the shape though. Alright, yeah, alright, so it's 28 by 28. And, okay, so the first thing we need to do is get its, PC representation. And so I believe the way we do that is with a matrix multiply. So, like we multiply by the PCs. So I think we say like matrix multiply the PCs, the real image, but we need to reshape it to be 28 by 28. And we need to transpose. Do we need to transpose? I don't know. Let's see what that does. No, it doesn't like that. What? Okay, so it needs to be like that. Okay. And then, okay, so, yeah. Alright, so like this is the PC representation, presumably, of our real image. So let's like visualize that, and then test to be sure, like the reconstruction, just to see if that works. But so first of all, let's just visualize the representation. And I think if you say like vertical lines, and then I just pass the PC representation, maybe. PC representation, what does that do? Oh, it doesn't like it. 2 required positional arguments. Maybe I want a bar chart. Is that what I want? Height. X. Okay, so I need to say range 0 to 28 times 28. It's like, come on, matplotlib. Do I just like reshape it to just to be 784 flat? No. Eager tensor. Oh, because I use TensorFlow. Whoops. Yeah, I should have just used, okay. That makes more sense. Okay, so, okay, so, yeah, so this, is there a way to make that larger, by the way? I mean, plot, yeah, I don't know how to make this larger. I just need to make it bigger. I'm gonna look that up real fast. Matplotlib figure size. You just call figure? Is that cool? I just call figure. and then I say fig size. All right. Figure, fig size. This is probably not going to work. Okay, that totally worked. That was amazing. All right, so anyway, this is these are the weights. So what this is saying is, like, if you want to produce this image, first of all, you take this image and you scale it by this giant, by 4, I guess. And then you take that other image and you scale it by whatever that is, and so on and so forth. Also, I think these things at the bottom are like, I think that's like numerical error, but I don't know what that is actually, because, yeah, I mean, like, if you look at them, like, they're just purple? I don't know, I don't know what that is. I don't know how to interpret that. So, okay, so let's test the reconstruction just to make sure. Reconstruct from PC representation. So the reconstruction, again, is a matrix multiply. And I think it's the... I mean, again, you're taking the principal components. I think you have to transpose them, though. But we'll take... Okay, so the PC representation. And then I think you... Or does it not allow you to transpose? I don't remember. I think you have to transpose these. And then you just show that. So... reconstruction, and it needs to be reshaped back into an image. 2828. Alright, hopefully that works. Okay, that's probably too large of an image, just, you know, just for future ref. Okay, this is the reconstruction, so I would say that that worked. And then you can also say, like, hey, what if we cut off, what if we only use, like, the top 100 weights, right? Because, like, these weights don't look like they're doing anything. So we're going to zero out those weights. So everything after 100 is now 0. And let's actually do that up here so we can show that also. So we're going to keep these and we're going to zero out everything from here. Okay, that worked. Okay, there you go. So it's like a weird, I mean, it like works, but it's weird. What if we keep a few more? I mean, weird. What if I only keep 10? Oh, cool. See, it's like a blurry version. Okay, so what we want to do is make a grid of images where we take, like, the first weight and we vary it between, like, 4, you know, and -4, or I guess, like, they go up to 8. So, like, between you know, 8 and -8, with, you know, some, yeah, and then so we're gonna take 2 of the weights, kind of like arbitrarily, and we're gonna generate the, like, see what the effect on the generated image is as we vary those weights. Okay, so it's like pick 2 weights to vary, display as a grid. It'll make sense. It'll make sense. So, okay, so I need grid code. So this is like grid code, because I don't want to remember how to write that, because that's annoying. Okay, so yeah, so what are we gonna do here? So we have a reconstruction, and well, no, okay, so we have the PC representation, and so I think we're going to, it's like we're gonna make two changes to the weights. I should probably call it the weights, but I'll just keep calling it representation. So these we're just picking arbitrarily. So we'll just say 0. And then we want it to be, so that's going to vary, say, like going across the columns. So I think we just want to say, we want it to vary. I mean, like, we're going to start it at like -8. And then we're just going to vary it with, I guess, like, based on the column. I think that makes sense. And so this will go, because there's 10 columns, it'll go from -8 to 2. And, I mean, like, we can fix that to be more different later. And so I guess the same thing with a row. And then we're reducing the reconstruction. So let's not do the 0 out thing. And so then, yeah, we're just literally creating the reconstruction. And then we're going to display it. So reconstruction, and we need to reshape it, I guess, to 2828, and these are supposed to be between like 0 and 1, so let's say like -1 and 1. Okay, so let's see what that does. Whoa. Okay, so that kind of makes sense, because the first principal component is this guy. So it's like this diagonal. What if I do 0, 1, 2, 3 as like the other one, to make that maybe look more different? Okay, so like this weight, make it 3. And also, we want to go from, so this needs to be like 16 divided by 10, right? Because we're going on a range. So this needs to be 16. Yeah, so that should be 1.6. Okay, so let's see if this is interpretable. Okay, so left to right, which, by the way, like, is that -8? Yeah, that should take you up to 8. I think that's right. So left to right is this splotchy image. So I guess that I mean, I guess like right here is like the actual image. But anyway, so going from left to right, we have that splotchy image. And it's kind of weird because like it kind of shows up as like a shadow effect here. But I mean, yeah, I don't really know how to interpret this. It's just for some reason it's highly visible here, and then as it scales, it becomes less visible. That doesn't seem like that's how that should work. But then the other thing is going down, you have like that center thing happening. You know what? Let me zero out the entire PC representation just so we can see what the thing is doing. So this is just purely those two weights interacting. Okay, so you can see here they kind of cancel out. That's weird. But like, I mean, it seems like the first weight, like this is basically the first weight. Maybe? Is that? Okay, let me, so it's like blue and yellow. Yeah, it doesn't seem to ever really like show up. Yeah, I got too much noise going on outside, so I'm gonna probably come back in a little while.